Okay, welcome everyone. We are 16 February and we are pleased to have Mr. McCalpin. Mr. McCalpin to give us a talk about paleoseismology. Before that, we have a short video to show you in 3 minutes.
Earthquakes are among the most devastating natural hazards in the world, often leading to catastrophic consequences for societies, causing loss of life, destroying infrastructure, and resulting in economic losses amounting to billions of dollars. So how can we design earthquake-resistant buildings that can withstand future shocks? And how do we assess the probability and severity of these catastrophic events? Generally, scientists have relied on historical earthquake records and instrumental data, based on the assumption that earthquakes of similar magnitude recur over time in a specific pattern. This is the field of seismic hazard assessment. But what if a destructive earthquake occurred long before humans inhabited the region? What if no records of the event were preserved, leaving our historical records incomplete? This is not uncommon, as historical records only capture a small fraction of the Earth's cycle, which can span thousands of years. This scenario has occurred in many places worldwide, where large earthquakes have struck areas with no strong historical records. For example, the case of Bumerdez 2003 in Algeria, Sumatra 2004 in Indonesia, Sichuan 2008 in China. To overcome this challenge, scientists turned to geologic records rather than human archives. Large earthquakes with magnitudes greater than 6.5 commonly leave lasting marks in the ground, rupturing faults at the surface and recording secondary effects in stratigraphic units buried beneath us. Nature has preserved many hundreds of thousands of years of seismic history. This discovery led to the birth of a groundbreaking science, paleoseismology. So what is paleoseismology? Paleoseismology investigates ancient earthquakes by analyzing their size, timing, and reoccurrence as recorded in young sediments. By uncovering earthquakes that occurred long before written records begin, it reveals hidden seismic cycles and helps refine hazard assessments in a scientifically grounded way. To explore this fascinating field, we are honored to host one of its pioneers, Professor James McCalpin, a major contributor to seismic hazard research, author of the seminal book Paleoseismology, and hundreds of widely referenced articles. Join us on February 16, 2025 for an exclusive webinar with Professor McCalpin. Discover the history of paleoseismology, its real-world applications, and its role in seismic hazard assessment. Take part in the Q&A session after the presentation. Ask your questions and get answers. This webinar is brought to you by Geohazard Community Group, a growing network dedicated to geohazard professionals and researchers, in collaboration with GeoLearnHub, an emerging platform committed to making geosciences accessible to everyone. We are also grateful for the support of the Research Center of Astronomy, Astrophysics and Geophysics CRAG in Algeria, which has helped make this event possible.
Okay. Okay, hello again. Hello, Mr. McCalpin. Hi. Before starting, Mr. McCalpin, we have a word from on behalf of the director of CRAG. He apologized for not being able to come today. He has a lot of occupations, but he sent us a word which our colleague Fouzi Bilalem from CRAG, senior researcher from CRAG, who is working on seismic hazard, he will read it to you. Fouzi, please go ahead.
Good morning, Professor Mr. McCalpin, and we are very joyful to join us
Fuzzy, please use a microphone, integrated microphone in your PC if you have, because the sound is far.
Okay. Good morning, Professor McCalpin, and we are very happy to join us to give this webinar, which coincides with the secondary anniversary of our group, Geohazard Community Group. So, on the behalf of the director of CRAG, Mr. Hamoud Beljoudi, who apologizes for being unable to attend this webinar. So he charged me to give this short talk. So the CRAG researchers are very happy to attend this conference, which is a great opportunity for them. The CRAG is a research center in astronomy, astrophysics, and geophysics, monitors the seismic activity of Algeria from two networks, a seismological network and GNSS network, and has seismologists, seismotectonics, and paleoseismologists who have been practicing since the earthquake of Al Asnam 1980. Thank you, Professor, for your conference. It's the word who the director charged me to give for this opportunity. Yeah.
Okay, thank you, Bilalem, for your word, and I'm happy here also to have on my side my colleague, senior researcher at CRAG, Saeed Maouche, who will animate this meeting with me along with Fuzzy. And now I will give a short biography for those who don't know Mr. McCalpin, although he is well known by his research. I will try to give a short biography for his important milestones. Okay. Dr. James McCalpin is a distinguished geologist specializing in paleoseismology and geologic hazards. His career began at the United States Geological Survey in Menlo Park between 1976 and 78, where he learned the emerging technique of paleoseismology. He later applied these methods during his PhD research at Colorado School of Mines between 1978 and 1981. Dr. McCalpin was a professor at Utah University between 1982 and 1991, before transitioning to full-time consulting, founding Geohaz Consulting in 1991. His work has shaped the global understanding of active tectonics, and he has directed over 190 projects for government agencies, regulatory bodies, and academic institutions worldwide. In 1994 and 1995, he authored Paleoseismology, the first comprehensive book on the subject, which remains a cornerstone in the field, with its second edition published in 2009. From 2019 to 2023, Mr. McCalpin served as president of the Inqua Terpro Commission, overseeing the PATA Days International Workshop Series. His extensive contribution to earthquake geology and hazard assessment have earned him numerous awards, including the E.B. Borwell Award and the Richard Jones Distinguished with over 185 scientific publications. He continued to advance the field through research, consulting, and international collaboration. Welcome, Mr. McCalpin, and the stage is yours to give your talk.
Okay, I'm going to try to share my screen with you. Here, here, and here. Well, thank you for having me present. Um, I have been in this science from the very beginning, and so this slideshow will start in the beginning. It will kind of pass through the boring middle and go ahead at the end to how the science is used today. When you have comments or questions, you should take note of the number of the slide if your question refers to one of the slides in the show. In the upper left-hand corner of each slide, the number of the slide will be shown. And so you could make a note to yourself that your question pertains to this certain slide number, and then I can go back to that slide and we can all see it when we are discussing your question. Well, paleoseismology is not like the normal new areas of science. It was not invented by professors doing what we call curiosity-driven research. Instead, it was developed to answer a simple problem that the engineering community was having. In the mid-1960s, we began planning nuclear power plants in the USA. And it was obvious that ground motion hazards needed to be assessed quantitatively so that we designed these plants to withstand earthquake hazards. In 1968, this became possible with the development of the probabilistic seismic hazard analysis code by Alan Cornell. And so you can see in the power plant, there are a number of vulnerable structures, these large cooling towers, and in the reactor buildings, some also taller circular elements that would be sensitive to ground shaking. So that's why we needed to assess the seismic hazards of these new plants. But there was a problem in the USA. We had only a very short record of historic and instrumental seismicity. And in the active Western United States, where the active faults were, this was only a 175-year seismic record. So many of the faults we later determined in this part of the world have recurrence intervals between large earthquakes measured in the thousands of years. So we had many faults in the landscape that were clearly young faults that had ruptured the ground surface, and those areas had had no seismicity whatsoever in 175 years. This was going to make it difficult to use the historic seismic record to quantitatively assess the fault hazard. Let's go to the first nuclear power plant that was proposed in California in 1958 at the Bodega Bay site. It's here, 80 kilometers northwest of San Francisco. This is the San Francisco Bay Area. Its 1960 population was 3.5 million. Of course, it's much larger today. And the San Andreas Fault is this red line here. And the San Andreas Fault was going within 3 kilometers of this proposed nuclear power plant. And of course, the 1906 earthquake on the San Andreas Fault had basically destroyed the city. So the Atomic Energy Commission of the United States asked the USGS to analyze the fault hazards to this proposed site. And the USGS concluded no faults active in the past 38,000 years and parallel to the San Andreas Fault passed through the parts of the site excavated as of June 6, 1963. Now, you will notice this is a very specific conclusion. It's very limited. It's not the kind of conclusion that instilled a lot of confidence in the Atomic Energy Commission, because there were all these caveats and limitations. They didn't say, oh, it's fine, there's no hazard here. Instead, they said something specific. If you want to read more about the background, there's this book here. But the Atomic Energy Commission looked at this language and they thought, you know, these guys aren't really confident that there's not going to be a low probability seismic hazard here. So they denied this nuclear power plant application. They basically told the Pacific Gas and Electric, why don't you look for a better place for this, where there's better, it's farther away from a huge active fault that has magnitude 8 earthquakes. So by the 1960s, it became understood that there were 3 types of seismic hazards: strong ground shaking, which would affect the reactor and the accessory buildings like the cooling towers; surface fault rupture, where the seismogenic fault propagated upwards all the way to the ground surface and offset the ground surface, and of course any buildings that were sitting on the ground surface; and shaking-induced ground failures such as liquefaction and landslides. Well, some of these hazards could be calculated by after 1968 because of the seismic, the PSHA code. Hazard A for strong ground shaking required input values for aerial seismic source zones at and around the nuclear power plant with an assumed rate of seismicity. In other words, the Gutenberg-Richter frequency magnitude curve and the A intercept and the B value slope of the curve, and location of active faults, which could be insert into the seismic hazard code as line sources, but they would also have to have their own magnitude frequency curve. Surface rupture hazard, hazard B, relied on the same data as above, but in addition, it would need to know the sense of surface slip on the fault, whether it was strike slip, normal, or right lateral, and the displacement per event, per large earthquake. Well, unfortunately, in the mid-1960s, seismologists could only provide the aerial source characterization, and even it was based on a short 175-year record of seismicity. At that time, there were no known faults, no known methods for locating faults that had been active prior to our historic record, or any way to assign those faults magnitude frequency curves, or any way to define the fault's maximum magnitude, maximum possible magnitude, or its sense of slip, recurrence, or displacement per event. In other words, there was a real lack of methods and techniques to quantitatively analyze the seismic hazards. And this was all pointed out for the first time in a fairly dynamic way by Caltech professor, this is California Institute of Technology, Professor Clarence Allen in 1974. He was the president of the Geological Society of America at that time, and his address was all about geological criteria for evaluating seismicity. any student or professor of paleoseismology or earthquake geology should be familiar with this, because it laid out in a better way than I could all the arguments for developing the science of paleoseismology. Well, of course, there had been historic earthquakes in the last, say, 100 years where the magnitude was much greater than 6.5. The fault plane ruptured all the way to the surface and offset the ground surface, creating what Richard Caputo of Italy called morphogenic earthquakes. That's earthquakes that leave a lasting geomorphic signature on the landscape. This one from 1891, one of the earliest ones, where we have a photograph of a fault scarp created by a large earthquake. Certainly the Japanese sent people out to look at this, but then they went home again. There was no community of paleoseismologists. There was no unified study of the topic. Really, the first attempt to quantify paleoseismology happened when the 1957 Gobi Altai rupture happened in Mongolia. And the Russians sent out two of their best geologists to look at this rupture. Mongolia was part of the Soviet Union at that point. And they were walking along the rupture that was only a week old when they got out there. And they noticed not only these very fresh fault rupture landforms, they noticed older weathered versions of the same things that were also on the fault zone. And they realized this was Florentsov, the geomorphologist, and Solenenko, the structural geologist. Florentsov said, hey, you know what? These old looking landforms, beat up, smoothed out, weathered, are evidence that there were similar earthquakes to this historic one in prehistoric times. And this really set up their system. This is Paleoseismicheskaya deformatia. This is Paleoseismic deformation is what they called their method. Unfortunately, in the USA, very people knew about these publications. So one of the reasons paleoseismology did not get developed in the 1950s is structural geologists were visiting these ruptures, but often not geomorphologists. And the structural geologists thought these rupture landforms would just erode away and they wouldn't become part of the permanent geologic record and be able to study them thousands and tens of thousands of years after they were formed. Radiocarbon dating required charcoal, which was scarce in deserts where many of these ruptures were happening. And besides, if they didn't even have the money, the dating was expensive and limited to about 35,000 years old. The fault plane was not itself exposed in vertical section. Usually what you saw was a scarp that had partially collapsed. And as these landforms of prehistoric ruptures became older, they smoothed out and they started to resemble possibly other non-tectonic landforms. So all the pieces of evidence that came together later were not all together in those early days. The first fault scarp that I visited in person was the 1915 Pleasant Valley, Nevada earthquake. This is in the USA Basin and Range Extensional Province. These are all normal faults in that province. This was a surface wave magnitude 7.6 earthquake. It made a 60-kilometer long rupture in 4 segments. This is just a piece of it, obviously. The maximum vertical displacement was 5.8 meters of the surface. And this photo was taken in 1983, so 67 years after the event. You'll notice it's not as sharp as the Gobi Altai photographs that we showed, which were taken a week after the rupture. But still, this feature is going to persist in the landscape for thousands of years, and we can study it before it completely erodes away. So this is what we call geomorphic evidence of paleoseismology. When the field was starting to develop in the early 1970s, the California geologists with USGS were talking to the engineering geologists. And the engineering geologists said, well, you know, I see you guys are mapping these fault scarps that were created by earthquake surface ruptures and earthquakes larger than magnitude 6.5. But why don't you trench these faults and see what the fault deformation zone looks like in a vertical cross section? And the USGS geologist said, that's a great idea. You know, we usually go out and look at the field evidence that's provided and preserved in the natural landscape. And engineering geologists say, yeah, we do that also, but we also trench to find where the fault is and to get more details on the fault. And this had never occurred to the academic community. They never trenched anything to create an artificial exposure. But this was the key part that was added to seismology, which allowed it to have two branches. One for studying landforms created by surface faulting, and the other to study trenches to be able to date the individual events and measure their displacements. And also with that, you could calculate the fault recurrence interval between large surface rupturing earthquakes and the long-term slip rate. So when I was doing my PhD, and for you students in the audience, most of the important advances in science have happened to PhD students between, say, 25 and 30 years old. Even Alan Cornell, who developed the PSHA seismic hazard code, did that as his PhD dissertation. And we are still using that thing, which he created in 1968 today. So when I was out there mapping these fault strands, that this is in the Rio Grande Rift of Colorado, an extensional rift zone, I noticed the landforms along the fault often looked like this. There was an older alluvial fan labeled BF, that's for the Bull Lake glaciation, the marine isotope stage 6 age fan, about 150,000 years old. And the next successive glaciation, the Pinedale, had an outwash channel down into the older fan. And then there was a single 2-meter high fault scarp that crossed both and offset both of these different age surfaces. And I went, okay, what is this trying to tell me? This is trying to tell me that this faulting event happened after the PF fan, the green deposit. It had to, because the fault scarp cuts the green deposit. And since this same fault 2-meter displacement affects this surface also, this is evidence that only a single event has happened since this Pinedale and Bull Lake surface. In other words, in the last 150,000 years, only one 2-meter displacement has happened. So it started looking like this, then the Pinedale channel was cut, then the faulting happened, and a single fault scarp displaced both surfaces. Well, it didn't always look like this. Sometimes you would go up to the fault and there'd be no channel. And so you just have the 150,000-year-old alluvial fan cut by a 2-meter fault scarp. All we can tell here is that that faulting event happened after 150,000 years. But it could be very much more recent than that. This could have happened 1,000 years ago in the Holocene. We only have a maximum age for this event. This fault could not have ruptured earlier than the Bull Lake fan, or we wouldn't even see it today. The surface would look like this. So it has to be younger than the fan, but there's no minimum age constraint. When we get to a situation like this, where the fault exists on the older surface, but not on the young one, there's been a 2-meter displacement. It's happened after the deposition of this fan, but before this channel was cut. So it's bracketed, its age is bracketed between 150,000 years and 25,000 years, which unfortunately is a low precision age because the time span that it happened in is very long. What we really want is a situation like this, where we have the older surface faulted, we have the younger surface faulted, but when we walk along the fault scarp and step up to the older surface, the scarp immediately gets twice as high. And we go, wait a minute, what did this? Well, this is easy to imagine. Just imagine this as a time sequence. We deposited the Bull Lake fan. We had a fault afterwards. Then the Pinedale Channel was cut. Then we had a second faulting event in yellow, another 2 meters of displacement, so that we end up with the Pinedale Channel only being offset by 1 2-meter displacement, but the Bull Lake Channel being offset by 2 displacements. The older displacement, the first event, happened somewhere between 25 and 150,000, and the second event happened sometime between today and 25,000 years ago. So this is evidence for 2 paleoseismic surface ruptures, each one of which is bracketed by ages on the maximum side and the minimum side. One of the first paleoseismic study sites in California was on the San Andreas Fault. And of course, the San Andreas Fault mainly has horizontal displacement, not vertical displacement. So the key exposure was at a place called Pallet Creek in Southern California, where Carrie C was walking through this step-over zone in the fault that had been filled with sediment. It was a little transtensional basin. And he noticed there were faults exposed in the gully walls that went up and terminated at a certain stratigraphic level. And this became a very important tool for determining when the earthquake displacement happened. It happened where the upward termination of the fault was. Well, it turned out to be a little more complicated than that. USGS trenched one of these faults that had just ruptured, and they proved that not every fault plane propagates upward to the surface in an earthquake. For example, on this cross section right here, which crosses these 2 strands, they obviously both come to the ground surface. But on this cross section, if you were to put a trench right here on BB prime, and this is what the trench wall looked like, you'd see 3 faults. You'd see this middle one come to the surface, and then the extension of this one, which died out, and the extension of this one that died out, they died out below the ground surface. You'll see them in the trench wall, and you'll go, oh, this is evidence for older faulting events. This one displaces today's ground surface, and this one happened earlier when the ground surface was here. Well, that's an incorrect conclusion. Actually, these things were beginning to lose displacement and basically lost all their displacement and died out up in the same displacement event that this one happened in. So die out up was something that people had to watch for. Most of the time you didn't have to worry about it. The fault came up to a certain level. It offset all of these beds. You can see this one got offset, this one got offset, this one, which is this one, got offset, and even this one got offset. The fault comes all the way to there. All of these beds were laid down after the faulting event had happened. So of course they're not offset by the fault. And this unconformity right here, which we call the event horizon, is the closest thing to date. This is the closest stratigraphic or structural feature that to date the earthquake. The earthquake happened after the deposition of this bed. This is the youngest offset bed, and it happened before this bed, which is the oldest non-faulted bed. So if you want to date when this earthquake happened, you get a radiocarbon or OSL sample from right here above the contact, and you get one from right here below the contact. And those two dates will bracket the age of the earthquake. Okay, so that's easy enough to understand. Sometimes it's a little more complicated. This was a fault here. You can tell that there was a fault because these beds are offset. Some liquefied sand squirted up along the fault plane and then spread out to the right and left. This is like a sand blow from liquefaction. But the next stratigraphic unit, the next two stratigraphic units, are also deformed over the sand blow. And that tells you, the ground surface was not here when the sand liquefied stuff came upwards. The ground surface was actually up here. And the sand coming up from beneath actually bowed upwards and arched upwards this unit. So the ground surface at the time of this earthquake was up here. You see, because this bed is not deformed in any way. So in this case, you wouldn't want to take the dating samples from either side of this contact. You'd want to take them from up here. Back in the early days, there was kind of a competition amongst paleoseismic trenchers to see who could see evidence for the most events in any trench. They were the splitters. They said, oh, I can see the evidence for 6 events in this trench. The lumpers were a little more conservative. They thought, what is the fewest number of displacement events that could have created the structures in the trench wall that I'm looking at? The minimum number. They were conservative. And Alan Nelson, a friend of mine in 2000, proposed, look, if you have a lot of upward terminations happening all at the same stratigraphic level, you can have confidence that they resulted from the same earthquake. The same for this one. You see all these faults terminate upward at this unconformity. A number of faults here terminate at this one. All these faults here terminate at this one. There are 7 upward terminations in here, all of which are at different levels. And he said, he was not a splitter, he was a lumper. He said, you can ignore these. They are probably all examples of die out up that formed when this earthquake formed, and most of the fault strands came up to the ground surface at the time of the earthquake, but these didn't. They don't represent 7 other earthquakes that you should try to interpret from this exposure. Well, about this time of year, the Ellis Nam earthquake happened in 1980. This was of great interest in the paleoseismic community. because we had very few reverse fault ruptures. And so the Earthquake Engineering Research Institute team was dispatched, and they studied this thing intensely. This was the reverse fault trace, as you well know. This was the hanging wall anticline on the upthrown block that contained the normal faults that were so prominent at the surface. This was very hard to see from airplanes flying over the site. This was easy to see. And so Mustafa, one of your former employees there at Crag, did a great study on these. This is the main thrust trace. This is the graben that was formed by normal faulting on the hanging wall anticline. And this was the trench that he dug. And this was one of the best trenches that had ever been made in the world at the time. This is a picture of the overhanging fault plane, which had ruptured to the surface in bedrock. Well, in 1983, I was in my second year being a professor, and a magnitude 6.9 earthquake happened within driving distance of my university. So my wife and I got into the car the next day, and within 36 hours, we were standing on the fault scarp. Here's what it looked like. She was 1.7 meters tall, so you can see that this scarp here is about 2.5 meters. Normal faults are the easiest surface ruptures to see because they're so steep. They're not like a reverse fault rupture like the LS Nam rupture, where the surface kind of rolls over and it doesn't even exceed the angle of repose. This is nearly vertical. But this is unconsolidated alluvial fan gravels. So this doesn't last long looking like this. This was only a day and a half after the rupture. We went back 6 years later, and the fault had started to weather. The free face, the part that is above the angle of repose, was weathering and shedding debris down and making this apron of coarse-grained colluvium, which was thick at the back edge and thin to a point at the front edge. So it had a triangle or wedge shape. And these had been seen in the trenches on the Wasatch Fault, and they were named colluvial wedges. And one of these wedges forms after every faulting event on a normal fault. The first things that fall off the free face are coarse grained gravels. Then when the scarp all becomes completely degraded and the free face disappears, as in this shape, material begins to wash over the fault scarp, and this is the wash facies colluvium. So here's this is an old drawing made by Robert Wallace in 1977, showing how these normal fault scarps in unconsolidated deposits slowly weathered back. The free face got smaller and smaller until it finally disappeared, and then it became a slower process of slope decline. And many geologists, it turns out, had walked past old fault scarps and thought they were erosional features. They didn't understand that they had been tectonic features at one point, and they completely ignored these things and their significance. And sometimes when building a colluvial wedge, you can, when looking at the colluvial wedge here after 3 surface faulting events, you can separate the 3 colluvial wedges because the older 2 have been faulted by the youngest event. So let's go through this from start to finish. The first event happens here. The free face is here. The free face erodes backwards on the upthrown block, making a colluvial wedge that is entirely composed of pieces of this stratigraphic unit. Then there's a second faulting hundreds or thousands of years later. It makes a bigger free face. This is now exposed in the free face. Pieces of this fall into the graben and make a second colluvial wedge. The first colluvial wedge got faulted by this second event, so now it's been dismembered a bit. Then there's a third faulting event, making this block even higher above this block. That exposes this unit in the free face. So the last colluvial wedge to get deposited is derived from this unit, and this unit. It mixes them all together. So, and each one of these, if there's thousands of years between these events, there is enough time for weak soils to develop on the surface of each colluvial wedge. So if you cut a trench across this today, you'll see an old wedge that has been heavily deformed. The second event wedge, which has been a little deformed. There's a soil on top of each one of these. And then the last wedge from the most recent event is not faulted, of course. It accumulated after the third event. And eventually it will also have a soil profile developed on it. So this is what you will actually see in the trench. And you'll use these three colluvial wedges and radiocarbon datable material from these trenches to date each event. This was one thing, the significance of paleosols in these fault trenches. Paleosols are ancient soils that developed at certain ground surface levels, and then that ground surface level was later buried by younger sedimentation, creating a buried soil or a paleosol. I was trained at the University of Colorado in quaternary geology and paleosols. And so when USGS came to me in 1977 and said, would you like to help log a trench with us? It was because they knew I could recognize paleosols as being separate weathering horizons, like a soil horizon. It's not a stratigraphic unit. It's a weathering profile developed on a stratigraphic unit. This particular trench log here shows something very indicative of the importance and significance of paleosols. Look at the radiocarbon dates from the shallow level here. 890 years before present, 0.11 Ka, that's kilo annum, that's 1,000 years. So that is 110 years. So these are very young dates. Dates from above this paleosol are in the 4,000 year range, 4.5. And then all the dates underneath that are much older. All the dates from strata underneath this soil, 117, well, there's something wrong with that date because the other two dates, 27, 44, and 35, indicate these sediments are about 30,000 years old. These are only 4,000 years old. There's a 30,000 year gap in the time record represented by the time of soil formation when this soil was forming. In other words, 75% of the time represented in this trench wall, 75% of the time is in this little soil here, which represents a depositional hiatus, a period of topographic stability. And clearly, during this 30,000 years of soil formation, there were no paleoseismic events happening. Otherwise, there'd be paleo earthquake colluvial wedges and scarp-derived sediment sitting on top of the soil. And that didn't happen until much later, until 4,000 years later. So this is a hugely important unconformity in the section. The early trenches that I went to in the Soviet Union which had been dug and logged by structural geologists. They had paleosols in them, but the structural geologists did not recognize what the paleosols were, and so they didn't even put them on the trench log. And I said, fellows, this is an important stuff. You need to go to another institute besides your Institute of the Earth's Crust and get a geomorphologist to help you log these trenches. And so that's what they did. And when I came back 2 years later in 1991, all of their trenches were much better. They were put in the right place. 90% of them hit the fault zone, and they had correctly identified and mapped the soil horizons. Okay, so people began to put together the geomorphic evidence and the trenching evidence to come up with some interpretational models. The first one was in the trenches by Schwartz and Coppersmith on the Wasatch Fault. The trench evidence showed repeated displacements had happened at a single trench site, and the displacements in each of the events was roughly the same, with no evidence for larger or smaller displacements. This was not only seen in the Wasatch Fault Zone trenches, it was seen in the San Andreas Fault Zone trenches, and also the geomorphic evidence that landforms along the San Andreas tend to be horizontally displaced either by 4 meters, or 8 meters, or 12 meters, or 16 meters. In other words, it looks like repeating 4-meter events with no surface rupturing earthquakes with smaller displacements than 4 meters or larger ones. So they called these repeating earthquakes characteristic earthquakes. They thought they were characteristic to each fault, the largest earthquake that the fault could generate, and it was restricted to a more or less narrow magnitude range. So let's look at a diagram showing how stress builds up on a fault. It builds up on a fault until it reaches this tau 1 level. That's the failure stress of the fault, at which point the stress on the fault exceeds the shear strength of the fault plane, and you have an instantaneous displacement which relieves all the stress back to some low near zero level. Okay, so stress builds up, reaches the failure stress. The failure stress is released in an earthquake displacement, which has so many meters of displacement, taking it down to a very low stress level. Then the stress level starts building up again. After that, it builds up and builds up and builds up until it reaches the failure stress level again. Then you have another big earthquake. Since all of the displacement events that they were finding in the trenches were the same size, they decided, you know what, this is a perfectly periodic model that's happening. They didn't really have enough dating control to tell whether the time intervals were identical, but they saw the displacements were identical. And they said, you know, the simplest model is that these faults occur on a regular basis and they're all the same magnitude. And this is called the perfectly periodic model of characteristic earthquakes. Well, later, of course, somebody pointed out, you know, they're not all exactly the same, the displacements. If you dig a trench, you do get some variation. Some faults have a lot of variation. The Wasatch Fault and the San Andreas did not, but some faults do when they were trenched. And so it looked like, well, the characteristic earthquakes ranged maybe from 6.5 to 7.1. They were releasing different amounts of stress. These are partial stress releases, and this is the time predictable model. If you know what the slow long-term slip rate is, and you know how much stress was released in the previous earthquake, you could predict the time when the next earthquake is going to happen. That's this horizontal time right here, you only released half of the stress here. So the recurrence interval till the next earthquake is only going to be half this recurrence interval here. And then there's another model which assumes the fault fails at variable failure stresses. So each one of these cycles of strain accumulation and release is called a seismic cycle. And the thing that begins and ends a seismic cycle are these characteristic high magnitude earthquake events. Another part of the model that they developed from the Wasatch Fault said, you know, from the trench dates, we see segments. We see the segments on the map here. This is a map view. So the Wasatch Fault is about 250 kilometers long. And it's got a little breaks in the faulting. And they thought, you know, maybe these things are rupture segments, because when people go out to examine recent surface rupturing earthquakes and they walk along and map the fault scarp, they realize the scarp did not rupture the entire length of the mapped fault. It only ruptured part of it, a segment of it. And so they said, you know what, we're gonna hypothesize that these faults don't rupture from one end to the other every time there's a characteristic earthquake, but they only rupture individual segments measured in tens to hundreds of kilometers. And that the boundaries between these segments are persistent. So segments never go from one segment into another adjacent segment. There's no partial segment or spillover ruptures. And this hypothesis of repeated partial length surface ruptures of segments was compatible with the repetitive magnitude of displacements in the trenches. So you can see on the Wasatch Fault, there are 6 segments, and they range from 30 to 50 kilometers long. So their model envisioned 30 to 50 kilometer pieces of the fault rupturing independently of the next adjacent segments. It turned out later, well, here's a rupture which was limited to a single segment. Its age plotted in calendar years, these are calendar corrected radiocarbon years, its age doesn't match up with earthquakes on either segment. It didn't go into this segment. It didn't go into this segment. It was a one segment rupture. But notice that this drawing, which was made in the early 2000s, is correlating ruptures that involved more than one segment. And this has become an important thing to incorporate into seismic hazard analysis logic trees, which is the way PSHA is done now, to allow for the possibility of both single segment ruptures and simultaneous multi-segment ruptures. Okay, so I don't know if any of you have any questions or comments up to this time, but if you do, I hope you remembered to write down the number of the slide that we're referring to, so that you can mention that in your question or comment.
Mr. McCalpin.
Yes.
Mr. McCalpin, do you hear me? Could you hide this message at the bottom of your screen? Not stop sharing, but hide it.
Sorry.
Because to allow more space. Thank you.
Sorry, I didn't realize it was on. Thank you. Okay, so now we are going to what happened between the 1970s and the 2000s or late 1990s. There were some methodological advances or interpretive advances, but basically everyone accepted the characteristic earthquake model and the segmentation model, and they just went out to trench every fault that they could possibly find. so they could find out the displacement per event, which would give them the magnitude of that paleo earthquake, and the recurrence interval, which could be turned into a slip rate. They weren't developing any new competing interpretive models, but there were a lot of faults out there to trench. So we spent the 1980s and 90s trenching faults all over the place. Meanwhile, there were some methodological advances, some things were noticed. The Nuclear Regulatory Commission commissioned a report to be written on techniques for identifying faults and determining their origins. This is a 466-page monograph, which was meant to answer the question, which kinds of faults could we or should we analyze in the seismic hazard assessment process? Should we only assess faults that can produce vibratory ground motion? In other words, seismogenic faults that penetrate the entire crust and that release seismic waves that cause strong ground motion? Or should we also include faults that will rupture the surface but aren't necessarily seismogenic faults? Here are the seismogenic faults. They both create ground motion and they rupture the surface. But there's a whole bunch of other fault-like features like landslides, sackung, sinkholes, volcanic dike emplacement that will create surface ruptures, but they're not tectonic. So they don't release strong ground motion. And they wanted to separate these groups out because obviously they did not want to place a nuclear power plant on top of a landslide failure plain. So this is a very important document for current earthquake geologists to be aware of. One thing that we inherited from the 1970s was a definition of a capable fault from the Nuclear Regulatory Commission. They said, look, we're only going to include in our hazard assessment faults that have moved in the last 35,000 years. There are so many faults out there that are older than this that we think it's unlikely. If a fault hasn't moved in 35,000 years, it's not going to move in the lifespan of our nuclear power project, which, well, we have many of them that are 50 years old now. So this was an assumption they made kind of to simplify life in doing the seismic hazard assessment, so you didn't end up analyzing thousands of faults which were seismically dead because the stress field had changed. But this caused a problem later. How do we know whether a fault in a trench has moved in the past 35,000 years? Well, let's look at, these are two examples where you can get a definitive answer to the question, has the fault moved in the past 35,000 years? Blue in all of these diagrams is pre-quaternary bedrock. It's millions of years old. The lighter colors are quaternary deposits that are overlying the bedrock, and they're either faulted or not faulted. Okay, so let's look at this one. You've got 10,000-year-old deposits that are faulted. Did this faulting event happen younger or older than 35,000 years? Obviously, it happened younger than 10,000 years, or this 10,000-year bed would not be displaced. So in a flow chart, you would ask yourself, are quaternary deposits present in my trench? Yes. Are the quaternary deposits faulted? Yes. Are the quaternary deposits younger than 35,000? Yes. So obviously, if deposits younger than 35,000 are faulted. This movement definitely happened after 35,000 years, which is, even older than this 10,000-year-old bed, and it's faulted. So this is a definitive yes. What about this case? Are quaternary deposits present in the trench? Yes. Are they faulted? No. Are the quaternary deposits younger or older than 35 Ka? Are they younger? No, they're older. So here you have bedrock overlain by a 50,000-year-old quaternary deposit, but that deposit is not faulted. Did the latest fault event happen before or after 35,000 years? You cannot tell from this diagram because there are no beds of 35,000 years at this site in your trench wall. Actually, no, that's not right. This is a definitive conclusion because the 50,000-year-old bed is not faulted. So clearly the last time this fault moved was prior to 50,000 years. So this is a definitive no. This is not a capable fault by the definition. All of these other instances, this one, this one, this one, this one, and this one, you get an indeterminate answer. For example, this one right here. You've got a 10,000-year-old bed in your trench, and it's not faulted. When was the last faulting event? Well, it was before 10,000 years, but it could have been 35,000 years. It could have been 50,000 years. It could have been 100,000 years. You cannot answer the question if this is what you've got in your trench wall. And so we didn't really, this is a drawback or a limitation of using a latest age of movement criteria for deciding which faults get analyzed in an SHA. And we're kind of stuck with it. All of the regulatory agencies, both federal and state in the USA, still use these kind of latest fault movement or most recent event age to determine which faults will get analyzed. Okay, let's go back to geomorphology evidence. This is again on the Sangre de Cristo Fault and the Rio Grande Rift. Here is the fault scarp. Here is the mountain range here. There's a major drainage coming out here. The fault crosses many different geomorphic surfaces of different age. The youngest one is down near the modern stream. This is a low terrace. This is a medium height terrace. These are older and higher terraces. And look what happens to the displacement on the fault. It goes from 1.4 meters here. It steps up to 3.8 meters on this low terrace. On this intermediate terrace, the scarp is 8.9 meters tall. On this old surface, it's 13.5 meters high scarp, and this scarp right here is 23 meters tall. What this is a story of is repeated fault displacement events through time, with this representing one displacement event, one surface rupture. This has been surface ruptured twice. This has been surface ruptured 3 or 4 times. And this tallest 23-meter scarp has probably been ruptured as many as 12 times, 12 2-meter displacement surface ruptures, which, of course, you could turn that into, if you knew the age of this surface, you would divide it by 12 ruptures to get the average recurrence interval. You could get the slip rate. You could get all sorts of information on fault, slip rate and recurrence interval and displacement per event without even trenching this fault. You would just get it from fault scarp heights. And this is what people did in the early days. In this particular site, I trenched this low terrace surface, and the trench did show 2 events. clearly in the trench wall. So this 3.8 meters was two events. It was this original, the latest 1.4 meter event, plus another 2.6 meter event that had happened before that. So not strictly characteristic behavior. I mean, those two numbers are not even multiples of each other. But this is the way it was done back in the 1980s and 90s. We developed a new problem once we started LIDAR. I think we could blame LIDAR on all of this, although if you'll look at this diagram showing the main seismogenic fault, the one that goes all the way down to the hypocenter, and then all these other secondary faults and types of secondary ruptures which don't penetrate the full depth of the crust and are not themselves seismogenic. I mean, they release negligible elastic strain. This paper was written in 2021 because people like the Nuclear Regulatory Commission and the people that built dams and other critical facilities not only didn't want their critical facility on top of the seismogenic fault, they didn't want it on top of this fault either. That's a surface rupture hazard, or on top of these faults. So they created a new category of faults called distributed faults or distributed ruptures. The principal fault was the seismogenic fault. All the secondary faults were distributed ruptures of one kind or another. Primary distributed faults actually intersected in the subsurface with the seismogenic faults. Simple distributed rupturing, these faults didn't, for all we know, they didn't even go down far enough to intersect and structurally connect with the principal fault. And they said, look, we need to know something about the probability of these kinds of faults occurring in the next surface rupture in an urban area or near a critical facility. We have to know the width of the zone that can be affected by this distributed faulting. And for you people, all of whom are very familiar with the LSNAM rupture and the diagrams and the trench logs, this was taken in 2021 by Fianen, who made this block diagram, from the LSNAM, because it had these bending moment ruptures in the hanging wall anticline. It had some back thrusts, that's what these are called. It had some subsidiary sympathetic or synthetic thrusts. So basically this diagram doesn't represent any one particular rupture. It represents all the possible ruptures, distributed faulting that you could have. And the International Atomic Energy Agency now has approved this approach to analyzing surface rupture hazards. How do they implement this? Well, of course, it's the day of digitization. So here's the faults that were mapped. This is the principal fault. These were 3 distributed faults. They would rasterize. The distributed faults happened in these grid squares. The principal fault happened in these squares. Then the probability would be the number of fault pixels, these gray ones divided by the total number of pixels. And what they discovered is that as you go farther away from the principal fault, the probability drops off of having a distributed rupture. As you might imagine, most of the distributed ruptures are close to the principal fault, and they do go out. And in this normal fault example, there were many more distributed faults on the hanging wall than on the footwall, which is common in normal faults. So here's a real life example. This is from the 2 databases that I'll talk about on the next slide. This is the Gulf of Corinth, earthquake 1981. These are the ruptures of Edgecombe, New Zealand in 87. Here were all the ruptures that got mapped. They chose this rupture right here as the primary fault. This is kind of an arbitrary assignment here. This is a fault swarm. It's hard often to pick which should be the primary fault when there's faults that are very similar to each other. But anyway, the frequency of distributed faulting was correlated with the distance away from the principal fault. You see, most of them are close in. There's fewer farther away. And if these field parties happen to measure displacements on these blue faults, these distributed faults when they were out in the field, we could also make a regression equation for not just the probability of a fault happening so many kilometers away from the principal fault, but the displacement on that fault at a distance of so many kilometers away from the principal fault. So this is what the data looks like in detail, and you can see those same patterns. Most of the distributed faults are happening close in, then they decline rapidly and kind of reach a constant level. This is 15 kilometers out away from the principal fault. Another advance that has recently happened is what they call portable OSL dating. That's optically stimulated luminescence dating. Back in 1987, when I first used thermoluminescence dating in paleoseismology, all of these dates from this trench, it had no carbon, and I thought, what are we going to do? But I knew somebody who had a luminescence lab at the University of Colorado, and I convinced him to come out, and this was the first trench ever dated by luminescence. It was thermoluminescence back in those days. But the problem was we had to wait 6 months for the dates to get processed. And of course, we had to backfill the trench by then. So I really wanted to know these dates while the trench was still open, and I could go back and look at them. Maybe some were out of stratigraphic order, and I'd want to go back and look, well, why is this a lower date younger than this upper date? But you could never do that. If you had to wait 6 months for the dates, no landowner would allow you to keep a trench open for 6 months. Now in 2021, a paper was published by taking a portable OSL reader to an outcrop and just pushing it up against the outcrop and measuring the luminescence directly. They measured 342 luminescence dating measurements in a day or two in this trench. So they didn't have to fill it up. They got the dates back in a timely manner compared to when the trench had to be filled in. This is a great advance, and there'll be more similar advances like this in the future. Using scarp heights, like that older example that I showed you, on older geomorphic surfaces which have higher fault scarps, streams are likely to deposit post-fault alluvium up against the toe of the scarp. This is the East Franklin Mountains fault in the USA. Here is an abandoned and faulted alluvial fan surface. The present alluvial fan deposition is going down this channel and building a fan out where these green arrows are. So the present drainage, this is abandoned as a depositional surface, and the present deposition is happening here, and then also coming down here and happening here. So when you measure the fault scarp heights here on this same surface, 10 meters, 9.4, 9.1, 10.1, 9.7. But when you get to the edge, the scarp gets much smaller. 5 meters, 2.6, 5.5, 2.4. Is the displacement actually decreasing toward the end of this fault scarp? No. The ends of this fault scarp are getting buried by tributary alluvium coming down and getting deposited up against here. So if you were to trench here you would grossly underestimate the amount of faulting displacement on this fault, and you would not be able to get down through these alluvial fan sediments. So you should never build or dig a trench out here in areas affected by this hanging wall aggradation. You should take the highest part of the scarp, but even it, you see there's a little alluvial fan right here. So it right here, the fault is only 7 meters high. Here it's 9.1 meters high. Even this, although it doesn't look like it, has been affected by 2 or 3 meters of post-faulting aggradation on the downthrown block. You didn't want to trench here either. We actually trenched here at the 9.8 meter scarp height, and that was the right decision to make. Okay, now the seismologists were not happy with us, and the seismic hazard modelers were not happy with us because we were digging trenches that only had 1 or 2 displacement events exposed in the trench wall. How many displacement events do you need in a trench wall to capture 1 complete seismic cycle? You need 2 faulting events, because you need to know when the cycle started and when it ended. You can't get a recurrence interval out of a trench wall that only shows 1 displacement event. There you only have half of the previous seismic cycle and half of the next seismic cycle, but you don't know when the previous cycle started and you don't know when the present seismic cycle is going to end. So you cannot compute a recurrence interval or a slip rate from a 1 event trench. And so they said, you know, you're just giving us a single recurrence number and a single slip rate based on a single closed cycle. That's not a statistically robust slip rate or recurrence interval. And we said, well, what do you consider statistically robust? They said, oh, I don't know, 10. If you had 10 measurements on the slip rate, we'd be happy. I said, wait a minute. You guys are asking me to dig a trench that's going to expose 10 events in the trench wall, and each of those events has 2 meters of displacement in it. So you're asking me to trench a scarp that is 20 meters high? And they said, yeah, is that going to be a problem? Well, we eventually figured out how to do it, but it was quite expensive. These are called mega trenches, and they were made just for the seismic hazard modelers, so we could give them an idea of the variation of recurrence interval on a fault through time. They didn't totally trust us to believe the periodic model of strain accumulation and release. They thought there had to be some variability in it, and it turned out they were right. The coefficient of variability is the standard deviation in recurrence or slip rate values divided by the mean value. So a coefficient of variation on a perfectly periodic system is 0 because the standard deviation is 0. But the numbers that you actually get out when you measure recurrence and slip rate from consecutive events, there's variability. The variability might be as much as, say, for recurrence, the average recurrence is 1,000 years, and the variability, 1 sigma, is 500 years. So the coefficient of variation is 500 divided by 1,500. The coefficient of variation is 33%. That's what the modelers wanted to know. It surprised us fault trenchers that it was that big. But now we realized why the seismic hazard modelers wanted these trenches. Unfortunately, these are very expensive to dig, so most faults don't have mega trenches on them. This one right here has 6 to 7 consecutive seismic cycles in it. And the problem with these big trenches is when you've had 6 or 7 displacement events rupturing to the surface over a 15,000 year period. Event number 2 faults the colluvial wedges that were deposited in event number 1 and kind of deforms them. Event 3 deforms both the colluvial wedges from events 1 and 2. By the time you get back to 6 or 7 events, the evidence of the early colluvial wedges has been deformed by 6 subsequent events, deformation events. It gets to be a real mess down there in the bottom of the trench. You're not really sure how to measure the displacement or what beds correlate across each other. So this was the first mega trench. I dug this in 1999, 66 meters long, 20 meters of stratigraphic section. But it contained things, deformation features in it that we've never seen in the smaller trenches, because you're creating quite a hill slope here, and parts of the faulted section are starting to slide downhill as if they were in a landslide, as if this failure plane here, the main failure plane, which is right here, was acting like a landslide headscarp. And we were combining gravitational deformation and tectonic deformation in the same part of the trench wall. And then the colluvial wedges were so messed up, we couldn't, for the earlier events, we couldn't figure out exactly when they happened. But if we'll go back to this previous slide, we'll see there's a bunch of fault-bounded domino blocks in here that have this pink unit in them, and then a bunch of stratigraphy on top of them. And the stratigraphy on top of them, each one of these blocks was different, indicating that these blocks had been faulted. Then part of the upper stratigraphy had been stripped off between the next faulting event. And so we actually put together the retro deformation sequence for this from the partial preservation in these fault-bounded blocks of the full stratigraphic column, starting from the very beginning and working, well, actually, you build a retro deformation sequence backwards from the present time to the past, rather than starting it and moving it forward. That becomes impossible to do. You do it backwards from the present back into the past. We got to see more things. This is not a very big trench, but this has also fault-bounded slivers, okay, each which contain beds that were kind of drug up from the subsurface and plastered against the footwall. So the stratigraphy can be traced into this fault zone. Then you can see how it's faulted. Then across this fault zone, these blue beds are faulted up to here. Then in the next fault zone, the uppermost bed in this fault sliver is green. It's this bed here. And then so all of these purple fault zones, they're somewhere deep underneath the trench down here, maybe down at this level. Then when we get to the next fault zone sliver, we can't find any beds in this sliver that correlate with any of the beds in this sliver. So these came from even deeper levels, tens of meters perhaps down below the trench floor. There's a long history here, but because once you cannot correlate stratigraphy from sliver to sliver, you can't include them in the retro deformation sequence. The other thing that this shows is that paleosols were mapped in this trench. There's a big paleosol. These brown units are paleosols, and these units are paleosols. So we mapped them separately from the stratigraphic units because we were concerned about capturing not only deposition, but the total time involved in the trench wall, which includes deposition time and soil development time. This was an experiment that didn't work. That previous trench was right here, and you can see there is a fault scarp here. I was worried that we wouldn't find charcoal in this trench. But there was a gully that had cut completely through the scarp. You see, there's no scarp here. And I thought, maybe there's some charcoal in these gully deposits. Let's go trench where there's no fault. Clearly, the fault is underneath this gully fill, and we should find it. Maybe we'll find some charcoal. So here's the trench. This is the gully surface. Here's what we found. Of course, it's exactly what we thought we'd find. We found the fault zone, and then about this is a meter. Okay, so about 1.5 meters of sediments of the gully that are all younger than the latest faulting event. And yes, there was charcoal in here. It gave very young ages, and we realized, what? This is not a good technique, because this is a huge unconformity. These beds are tens of thousands of years old, and these beds are only 2,000 years old, and an unknown amount of these older beds got removed by erosion. So there's a big time gap here. And actually, the dates that we got from the bigger trench back here were older than this, telling us that this was a minimum age and not a very closely limited minimum age. So it wasn't very useful. The tighter constraining ages came from this bigger trench. We found the charcoal, but it didn't really help us tighten the age constraints on the latest 1 or 2 events. Well, not everything you try works. I guess that's the moral of the story. Here's another story we learned when we trenched and discovered things in the trench that we didn't anticipate. Sometimes people have dug paleoseismic trenches and not found a fault. And then it became obvious to them they put the trench in the wrong place. Is there any way to prevent that from happening? Yes. You do geophysics before you trench. One of the early things that structural geologists asked me is, well, okay, these are very nice trenches you have, and there's a very nice way to work out the recurrence interval and the slip rate and the displacement per event, but how did you know where to put the trench? And I said, well, I'm a geomorphologist. I went to a place where I thought there'd be datable charcoal, and so I was looking for a sediment trap like a graben, and this was before OSL. Nowadays, you can almost trench anywhere and get OSL samples to date, but this was before that. And but sometimes people would miss the fault entirely. So we decided to do geophysics. We wanted to know what was deep under the ground, and we would use this to decide which of several possible trench sites we would trench. Maybe we only had enough money to dig one trench, and we didn't want to dig it in a bad place. We wanted to dig it in the best place, and geophysics would tell us where the best place is. Obviously, the big fault in this is ERT SSR. I'm not sure what they mean by SSR. It's not GPR. But anyway, obviously the big anomaly is right here. So you don't have to dig a very long trench looking for the fault when you have the geophysics tell you exactly where the fault is. We used to dig trenches hundreds of meters long because we weren't sure where the fault is. We could have saved a lot of money in trenching if we'd done geophysics first. Well, very large scarps. Now I'm talking about scarps that are over 100 meters high. Fault scarps over 100 meters high, like this one. This is in the Rio Grande Rift. The bedrock at the surface here is a 1.1 million year old welded tuff, andesite tuff, so it's very hard. And the fault scarp is 110 meters high. And the client, the Los Alamos National Laboratory, where they designed the first atomic bomb, that's this plant complex here, was built right up to the toe of this fault scarp, only they didn't know it was a fault scarp, or they never would have put the plant here. And when they finally figured out this might be an active fault scarp, the thing was already built, and they wanted me to trench this 110 meter high fault scarp, thinking that it was just a scaled up version of, say, a 3 to 5 meter fault scarp with the fault in the middle of the scarp and etc. And I said, well, wait a minute. We've got bedrock at the surface here, and we don't really see where the fault is. Let me map this fault to make sure that I know where to bring the excavator to make a meaningful trench. Well, it turned out it was a good thing that I did the mapping, because this is what it looked like in cross section. There wasn't a single, this is the scarp face. This is the up-thrown block and the down-thrown block. There was a little graben here, but the scarp face was not underlain by a fault, like it is when you fault on consolidated deposits. This was basically an articulated monocline with a nearly flat-lying block, a forward tilted monocline core, a little fault here, and maybe a half graben here. And this is not to scale. I mean, this is 50 meters vertical from here to here, and this from here to here is only 5 meters. So this is most of the scarp height right here. If I had brought the excavator up and started digging here, I would not have found a fault. What I was afraid is that if this was just a scaled up geometry from like a smaller fault scarp with the fault in the middle, there would be a 50-meter thick colluvial wedge here. I couldn't dig through a 50-meter colluvial wedge, not with any excavating equipment known to man. And so I was kind of glad that it turned out this way. But our trench target became mainly this big tension fissure, which was created by the monocline slab tilting forwards and this thing pulling away from this thing. Here's the trench in this tension fissure. So sometimes when you use geophysics and mapping, you get a much better idea of where you ought to put your trench. I don't know if you know this word Sakung. These are uphill facing scarps and grabens that were originally described in the Alps, in glaciated valleys. When the glacier oversteepened the valley walls by erosion and then retreated back into the cirques, leaving this oversteepened wall unsupported because the ice wasn't here anymore, this whole ridge spread and extended laterally, putting the ridge crest in tension. And this tensional stress field was accommodated by the development of normal faults, including uphill facing scarps and a central graben right along the ridge. And for many years, people thought these were tectonic fault scarps, seismogenic fault scarps. Okay, well, there were actually two groups. One thought they were purely gravitational features, which did not extend down even more than a couple of 100 meters into the crust, and others thought they were true seismogenic faults. So we started trenching these things in the late 1990s. Here was one of the ones. This is in British Columbia. It was so long and linear, the Geological Society of Canada called this a recent fault. a tectonic seismogenic fault that could produce ground motions. But some of their own employees disagreed with this. Well, this was an old map. This was a younger conclusion. They said, you know what these are? These are just gravitational sakungs. They're not seismogenic at all. This one in particular was using an old bedrock fault plane to gravitationally spread. So when you dug a trench across it, you found all sorts of faulting and shearing, but that faulting and shearing had happened a long time ago. And this example that I'd used before was actually a Sakung trench. It was, here's the Sakung scarp right here. It's created a half graben right at the very crest of the mountain range. There is a tectonic fault at the toe of this steep range front escarpment, just a normal basin and range seismogenic normal fault. But this fault split the crest of the range. And Bob Wallace in the 1970s said, you know what, I think this is a Sakung. I don't think it's a seismogenic fault at all. He was very ahead of his time in that conclusion. So this goes back to the two overlapping circles from the Nuclear Regulatory Commission. You've got to be able to separate these things which produce seismic ground motions from things like this that can rupture the surface but don't produce ground motions. So conclusions, of course, more work needs to be done. In geomorphic expression, we don't have LIDAR all over the world, and so it has shown us many things, especially in heavily vegetated parts of the world. We are finding scarps that we didn't know existed because we couldn't, aerial photographs could only see the top of the tree canopy in the forest. We couldn't actually see the ground surface. Stratigraphic expression, always do geophysics first before trenching. You can dig large trenches, but they're expensive. You can extend a smaller trench by bringing a drill rig into the trench and digging or drilling into the floor with the drill rig. That's kind of a pseudo trench, but it's cheaper than trying to dig a 20-meter deep trench. Dating displacement events, well, we're going to get OSL and things even more recent than OSL. Probabilistic seismic hazard assessment and probabilistic fault displacement hazard assessment. We now realize we need better post-rupture mapping using LIDAR and drones. When we go out into the field, we need to be able to pick up all of the secondary distributed ruptures that happened before they get erased by erosion and you can't see them anymore. And if we do that, then we can increase the database, and the equations that we use for distributed faulting will be much more robust enough that engineers will actually use them for design, which at present they do not do. It's sad to say, but it's true. Okay, so I thank you for attention. I'm going to quit sharing my screen now, I think. Yes. Let me go to here.
Thank you very much, Mr. McCalpin, for this wonderful and good presentation.
So I'm going to hit stop screen. Is that right?
Yes, stop screen. You can. Yes.
Okay.
Yes. Thank you very much for your beautiful presentation, and I think you're done, Mr. McCalpin. You don't have something else to.
No, I decided not to do the LIDAR thing. It would take too much time. It would take time up that I would rather use to answer questions.
Okay, before going to the Q&A session, I would like to apologize for those who couldn't join us via StreamYard platform. we have a technical problem that we can't allow more than 10 seats here, and they can watch the presentation, which is recorded in the Facebook and YouTube channels of GeoHazard community and GeoLearn Hub platforms. Now, I would like to welcome Miss Maria Teresa Ramirez, which has done a lot of efforts to spread the word, and Mr. Frank Odimar, which is now with us live, and I will give and Mr. Fouzi Bilalem, of course, and welcome. And I think we can start the QA session. If there is any question from the audience on Facebook or on YouTube, you could put it, any question related to the topic.
Frank, long time no see.
Hello, Mr. Odimar. How are you? You can activate your microphone, as we can hear you.
Yeah, it's done. How you doing, Jim? Pleasure to see you.
I'm hanging in there, but I've lost some hair.
You're
from
trying
the last
to look
time
like
we
me.
saw each other.
Miss Teresa, you can unmute your microphone, as we can hear you. Yes.
Yeah. Hello, everybody. Thank you so much. I want to thank Jim for this wonderful master seminar. It just covered everything. It was absolutely amazing to hear you. I don't know if I can ask a question right now, or I should wait for.
Yes, yes, you can.
Okay. Well, it's a comment and also a question, because I think you tried to cover and did cover a lot in the field of paleoseismology. I just want to point out that, there is also, what do you think about the coastal paleoseismology, and also the submarine paleoseismology that is being done a lot of work in the Cascadia subduction zone and also in Japan and the coastal one. And I just want to also ask for your comment on, I know you summarized at the end some of the tasks that need to be done for the future, but I'm sure we have a lot of young students now working on their thesis or projects, and it would be nice if you could tell us what do you envision as the fields that need to be done and could bring more information in terms of paleoseismology. Thank you.
This is a good question because an old guy like me who started out early, we are very fault centric. We are always looking at the fault evidence, and we have not paid as much attention to the secondary evidence of paleo earthquakes, like liquefaction, earthquake-induced landsliding, sagungs being triggered by earthquake ground shaking. So I think we have not spent enough time on these secondary effects. These are the effects in the environmental intensity scale, for example, that was developed about 10 years ago. And I think that for faults that do not rupture all the way to the surface, that there is no on-fault evidence. The only thing we are going to have to work with is the evidence created by shaking, the liquefaction, the sackungs, the earthquake-induced landslides, and things like that. And these may eventually someday allow us to detect earthquakes smaller than magnitude 6.5 in the 6.0 range, even in the 5.5 range. And they would be the only thing that would allow us to detect blind surface ruptures that where the rupture did not even make it to the surface. Those same comments would also apply to the submarine paleoseismology. And, it's funny, for many years in early seismology, we would look at a fault drawn on land and it would end at the water body. It would end at the shoreline. And we said, okay, so the fault ends at the shoreline. No, we never thought, of course, the fault doesn't end at the shoreline. That's just where the map stops. The fault extends offshore. And in a way, this is like the secondary shaking effects that you see on land. The submarine things, you can't go down and trench them, obviously. You're going to have to use different techniques. They will yield a story. They will yield a turbidite story. You can see them on geophysics. We'll never be able to get down and trench them, but we can drill them. Drilling and coring of submarine fault scarps has allowed to date the unfaulted vents, the unfaulted stratigraphy and the faulted stratigraphy, and bracket basically the upward termination of the fault underwater. So some of the on-land techniques will work. We'll have to develop more submarine techniques. Submarine techniques are expensive. You can't just hop in your car, drive out, and go trench a fault. You're talking about a ship, a whole crew, a coring apparatus, all this other stuff. But if it's important, hopefully the money will be found.
Thank you.
Frank.
Yeah, Jim, excellent talk. You went through many things in a very short time. And Maria Teresa, nice to see you too. Maria Teresa is very fond of tsunamites. She's been working for quite a while on the Pacific coast of Mexico. And that's a way of approaching offshore faults as well, by tsunami records. So I congratulate her for her work on that. I wanted to point out several issues, several things you brought up, which are very important. One thing, anecdotic, your colleagues, your American colleagues, started playing and exporting your expertise to Venezuela in 1968. Your friends Clough and Hansen made trenches on Oka Fault in 1968 and published it in 1969 for a private oil company report. Very nice work. They determined that the Oka Fault was active in 1968 by trenching. So you can include that in your roster of all works. It's been
those reports are never published.
Yeah, they were never published, but I made them public in my PhD thesis.
Oh, okay, great.
And yes, and was also reutilized in a couple of review papers. So you can have the data whenever you want. So 1968, you were walking across the Caribbean or sailing across the Caribbean, and doing paleoseismology in Venezuela in 1968. So it's among your first works around the world. The other thing you touched, and I find interesting, when you want to complement a trenching study, coring, drilling is a very useful approach tool. So I recommend it too. I used it a couple of times. It's very complementary. It can help you to open up the stratigraphic record. It's incomplete in your trench. The other thing you touched that I think is very important is, and I developed that for my colleagues, my younger colleagues in Fumvisis. I used to have a good eye for trenching sites, but the younger generation, they are not so good at it because maybe they are not good enough in combining, as you said, geomorphology with geology. It's it's more than combining geomorphology and geology. It's combining geomorphology with stratigraphy and sedimentology to find the right place when you are trenching. And you gave a good answer to that problem. Geophysics ahead. Geophysics, you have two techniques which are very helpful: GPR, ground penetrating radar, and electric tomography. You can get very good results for on fault trenching. I suggest, because as you said, it reduces the ambiguity where the fault is. You give more precision where the fault trace is. It's very useful. We started in Venezuela trenching 80, 90 meters long trenches, and then we became so good that we could do it with 10 meters long trenches because GPR or tomography could reduce the size of the trenches. Yeah. It improved quite a lot. And you said something very useful too. Whenever you have an active fault with recent rupture, go across it. Do as many trenches as you can across those new rupture surface. It's much easier to know where the fault is because you have the evidence few days on, very young evidence. So those are the targets we have to follow. As soon as you have a rupture, go and trench it where you think the record can be complete. I agree with you. That's something we have to do. And as Maria Teresa was indicating, we have to leave a little bit on fault trenching and go further for the shaking evidence. I agree with her. There is a lot of work to do there. And one thing that is important there, as you decide to start studying off-fault evidence, you have to think that you are trenching, or your trenching has to be like a seismographic network. It's not, you are not cutting the rupture itself, so you need to understand the earthquake as if you were constructing a seismographic network. You have to trench as much as you can where the evidence are related to a single event. You have to relate all those features to one event to make sort of macroseismic model. So it's quite a big work ahead. So I think it's a field where pretty much has to be done yet. But congratulations, Jim. You've been a pilot there, a cornerstone in paleoseismology for quite a while now. Thank you for your talk.
You know what, Frank? We want to see you at the next PATA Days.
Yes, I
the
wanted to go, but I'm a retired man and I have no money. I'm not like Geohazard, who is a private consultant who makes a lot of money. I'm a public retired guy. So if I'm not invited, I have no means to go.
Okay, I have
Sorry
some
for
good
that.
news for you. The next Pata Days in 1.5 years will be in Guatemala,
Oh,
closer to
are we
you.
going to Motagua Polo Chic with Christoph, who's trenching around?
Yes,
Yes.
Oh, excellent! Because Isabel
yes,
Lake and the
Motagua.
trenches, Isabel and the trenches should give us a good story.
So we want you to be there.
I'll try to be there. Thank you.
Excellent.
Hi. Hey, Yahya.
Okay, thank you, Mr. Odemar and Mr. James. Said, do you have anything to add or comment
Yeah,
before getting on?
maybe a
Yeah.
small question or comment. No.
Yes.
So, Professor Jim, thank you for the very interesting talk. Yeah, it's a really pleasure to learn about this method. No. So, as we say, we trench to constrain the timing, location, and size, no, of past surface rupturing earthquakes. No, so in such case, the geologists can therefore reveal what happened in the past. And how, and we say also the best seismologist is the one who finds active faults where least inspected. No, and the question of timing, and also the timing, so the occurrence or the date, and I don't know if you can give your opinion on the evolution of the dating methods, for example, which are the source of several uncertainties, particularly the dating performed during the last century.
Well, I'm not a laboratory geochronologist, so I
Yeah,
don't actually do the dating myself. But I will say that the scientific literature is full of old dates which were never redone with more modern methods that are not so accurate. So they are in the published literature, but if we were to re-excavate that trench today and use modern methods, we would get different numbers. And this is
exactly.
not only true of dating, it's true of many early trenching investigations. They weren't done the way we do it now. Uh, there's a famous trench site on the Wasatch Fault. They dug a big trench. They couldn't find any carbon to radiocarbon date. They only found one little piece. So they had one date out of this huge trench, and they published the paper. And 10 years later, I read this paper and I said, I think there's something wrong with that date. It's too deep below the ground surface and too young. It's too young to be that far down below the ground surface. And by this time, luminescence dating had started to become common. So I re-excavated the trench and I took 10 luminescence dates out of it. And they showed they were all in correct stratigraphic order with the youngest at the top and the oldest at the bottom. and the original carbon date from 10 years ago was a complete mismatch to the OSL dates. And so that paper was completely wrong. But
yeah. Yes.
Did the time OSL dating didn't exist. So I just would warn people that are we still connected?
Is there any problem? Do you hear me, Mr. McCalpin? I can't hear you. I don't know if it's on my side, the problem.
I hear you. I hear you. No?
You hear me, Said?
Yes. But now
The others, I think James has got
something
problem.
happened. Yes.
Yes.
Something happened.
We will wait a little bit.
Fauzi, are you here? No.
Yes.
Frank? No. Maria? No.
No, they are unmuted. They are unmuted. Yes.
I'm here. Yeah.
Welcome.
Thank you.
I think the signal is coming back.
Yeah.
Technical problems, no?
Yeah.
Jim, are you back? Your image is frozen.
James.
Professor James.
Uh-huh.
He's coming.
We're coming back slowly, smoothly and slowly.
Yeah.
Activate your microphone, Bilalam.
Okay. Est-ce que vous me reconnaissez?
Oui, un plaisir de te revoir.
On s'est vu à Fucino. Je suis désolée de parler en français parce que mon anglais est très limité. Donc, si tu peux traduire pour moi aux autres membres, je vais parler de Maria Teresa et James McCalpin, parce que je voudrais informer vous et les gens présents ici que actuellement nous projetons de lancer un projet que nous allons commencer incessamment sur justement le bassin du Chérif, là où il y a eu la faille d'El Aslam de 1980. Et donc nous voudrions faire une réinvestigation de toute la région qui contient la faille principale qui a donné le séisme de 80, mais également d'autres failles, et cette fois-ci, puisque les études qui ont été menées à l'époque suite à l'avènement du séisme de 80, il n'y avait pas toutes les méthodes nouvelles de géomorphologie, de morphotectonique, de géophysique comme il en existe actuellement. Donc nous allons réinvestiguer
Et ce projet aura des fonds européens, des fonds locaux, combinés. Pour quel moment vous pensez que vous pourriez le lancer?
On est en ce moment en plein lancement. C'est vraiment le début parce que c'est un projet local. C'est-à-dire
Ok.
que c'est un projet
Avec des fonds.
algérien qui est enregistré au niveau de notre centre de recherche.
Ok.
J'en suis la personne qui essaie de coordonner à l'intérieur de ce projet. Il va y avoir des partenaires français avec nous. Nous espérons également, en plus de faire toute la réinvestigation, géologique, géomorphologique notamment, et paléoseismologique, nous espérons réouvrir peut-être les tranchées sur la paille principale, mais sur des pailles dans la région. Il y en a pas mal pour les gens qui connaissent un petit peu le sujet. Et bien sûr, nous avons aussi beaucoup de données en ce moment, des données qui sont issues de 2 grandes compagnies en mer qui ont
ça serait un projet de quoi? De 200 par 200 km? Est-ce que vous avez une idée? Si vous comptez inclure la côte et descendre jusqu'à Chelif, ça va être 300 bornes, 400 bornes?
Mr. Odimar, Mrs.
Yeah,
Haddad,
I'm gonna translate.
because people here are not familiar with the French.
Yeah, but she's
and,
asking.
And Mr. James McCalpin is come back. Yes,
she's asking me to translate into English what you are proposing. So, in few words, Jim and Maria Teresa, the Algerian colleagues are trying to put together a new project to reevaluate some regions in Algeria from Chelif, where the Asnam earthquake occurred, up to the coast in the north. So they may be interested in our participation in this project. It's a project that they are trying to bring together with Algerian funds. I know this been going for quite a while because we have been in contact several times on this respect with the Algerian colleagues, and they are putting together a project with local money, local funding, and maybe they would like our expertise as part of the team. What do you think about? Your microphone is off.
Your microphone.
It's on.
Okay, how's this? Better? Can you hear me?
Yes.
Yes.
So sometimes
yes,
sometimes I have been brought to trench sites already dug, and they just want my opinion of what's in the trench. And sometimes I am asked to help suggest where the trench should be. Those are 2 very different things. One, I come in the beginning. The other, I come only at the end. So it depends on what the local people want.
Mr. McCalpin, I think there is a question in the comments. We didn't get a lot of questions in the social media. We have a question, but it is related to African origin plates earthquakes. Do you want to answer such a question, or we give the answer to Mr. Odimar or Said Maouche? I don't know if this is related to African origin plates earthquakes in North Africa.
I am not the person to answer questions about your fold and thrust belt.
I'm not the specialist of the region, but in a single answer, we could say that the entire atlas across the northern coast of Africa relates to the collision between Eurasia and Africa, and is essentially compressional, such as the Lasnam rupture, or those we've had offshore Morocco, or even Tunisia as well. So it's the typical compressional setting of a collisional origin, I would say, in short words.
Thank you. Is there any other comments or suggestion or question? We are open. Those who are not in StreamYard, if you want to, if there is a senior researcher here and now following us and want to speak with Mr. McCalpin or make a comment or ask question, please come to the StreamYard studio, which allow up to 10 persons. We have 2 or 3 seats for you if you would like to join. And we apologize in behalf of GeoHazard Community Group and GeoLearn Hub. We apologize for this inconvenience, and we couldn't fix it at time. So people are following us from social media, not from StreamYard. Said, are you here? If there is no more questions, Madam Haddar, Miss Haddar, do you want to add something or question, or continue?
Not question, but only information to inform our colleague that je voudrais continuer sur ce que je disais tout à l'heure, Monsieur Audemars, que vous m'avez demandé quelle est la surface, la superficie du projet. Le projet pourrait prendre quelques 200 km sur 200 km, parce que le bassin, en fait, vers le nord du bassin, il y a la limite offshore. Et offshore, nous avons des données. Actuellement, nous avons une banque de données importante offshore qui nous permet de faire le lien entre la tectonique active terre-mer. Et vers le sud, nous avons bien sûr une limite vers des structures anciennes, plutôt des formations anciennes. Donc, nous espérons également faire la modélisation onshore, offshore de cette région. Donc, il y a beaucoup à faire, surtout que la paléoseismologie, comme vous le savez, en Algérie, elle a commencé très tôt avec le séisme d'El Aslam, mais elle a connu un large épisode où il n'y a rien eu entre-temps. Ce n'est que vers le début en 2011, où nous avons entrepris de reprendre la paléoseismologie, cette fois-ci dans l'Algérois, pas loin de la capitale, où moi-même, en collaboration avec des collègues français, nous avons effectué une tranchée de paléoseismologie sur les failles secondaires. Nous n'avons pas tranché la faille principale de la structure du Sahel qui longe vers le sud de la région d'Alger, parce que cette faille est...
Miss Haddar, could I translate? Yes, could I translate the most important about your talk to Mr. McCalpin and to make him into the debate? Miss Haddar is the head of seismotectonic team, and she is explaining an upcoming project around the Asnam, historical Al Asnam earthquakes, not only the Asnam fault, but the whole region of Shelif Basin. And she is asking and given an issue about trenching thrust faults in Algeria. We have a lot of thrust fault system, and the problem is not like the normal faulting system where beautiful fault scarp are well preserved and we can choose where to trench. And I think here, because Mr. McCalpin is here, we would like to ask him about. I know he hasn't worked a lot on thrust faults, but if you have some advices about trenching within our context, where the active faults are slow slip rate and there are a lot of area of deformation, as you mentioned before. Mr. McCalpin.
So your project is only going to be in a certain part of Algeria?
Yes, the Shelif Basin, yes.
Okay. Do you have LiDAR of the whole basin?
No.
Well, you're going to need LiDAR because it's going to be much harder to find the fault traces on reverse faults than on normal faults. And so you are going to absolutely need LiDAR of the area you want to study.
It depends. Maybe the areas that we are working are essentially desertic, so the canopy is not important. So it is more a morphological, conventional study for looking for reverse or thrust faulting. In that case, we've got in Venezuela a certain experience along the Andes, not only in Venezuela, in Colombia and in Argentina. But I believe Shelif is more like Argentina, is bird, is unvegetated. So it's more like looking for faults in Argentina than in Venezuela and Colombia, which is tropical and a very important canopy.
So right now, what is the best resolution digital elevation model of the area you want to study? Is it 1 meter, 5 meters? What?
How many the resolution? Yahya, the resolution, la résolution à l'INCT, la meilleure résolution que tu as. Tu peux leur donner?
DEM, Digital Elevation Model. Yes, we have 12. We have 12 meter spatial resolution.
12 meter. Can you
12.
repeat? 12 meter.
12 meter.
Excellent.
Yes. Yeah.
And were these 12-meter digital elevation models made from old contour maps? What were they made from?
No.
What was the data store?
They are from pulsar mission.
Pulsar imagery.
Yes.
Pulsar.
Okay.
Pulsar. Yes.
12 meters.
It's not.
That's excellent for me.
Excellent.
Well, then you go to Algeria, Frank, because
I have no problem.
I am spoiled. I want 1 meter LiDAR on all my projects.
You work in the first world.
Well,
I'm used to the third world.
Okay, so we'll just do it with aerial photographs.
That's great, huh? Even better.
No problem. I have something.
The only problem we have is with those faults offshore in northern Africa. There are several which are hidden underwater. They have had several large earthquakes in the last decades, and they are offshore on the northern side.
You recognize this?
Yes. Yes. A stereoscope.
Yes. Of course.
Fundamental device for geomorphologists.
From the early Pleistocene.
But they are still very good.
Okay, no problem.
Professor McCalpin, I have a short and quick question to Professor McCalpin. So I'm not the expert or specialist in paleoseismology, but I have a curious question. Do recurrence intervals differ from normal strike and reverse faults? You heard my question?
I only heard part of it. I think my internet signal is getting interrupted.
Mine too.
Do recurrence intervals differ or varies from thrust fault, normal fault, or strike slip fault?
Are you talking about trenching or mapping?
No. About recurrence intervals.
Yeah, they are different.
Of course, they're very different. The normal faults are easier to map, and they don't hide. They don't hide like reverse faults. They even strike slip faults are sometimes difficult to map. So I would say normal faults that I have talked about mostly today are the easiest to work on. They're the easiest to find good trenching spots. You can do it with imagery. Reverse faults are sneaky little faults. They're trying to hide from you. You must hunt them down like a hunter. And the trenches that you dig across a reverse fault have to be started up on the hanging wall to make sure they intersect the fault, which of course is dipping, the fault plane is dipping back underneath the fault scarp face. So you have to start it in a different place. And its deepest part needs to be underneath the crest of the fault scarp. In normal faults, the deepest part of the fault is under the toe of the fault scarp. But this is well known. This is normal procedure for trenching reverse faults.
Okay, thank you.
Okay, thank you, Mr. McCalpin. I think we arrived to the end of this meeting. We won't get more of your time. You were very generous accepting giving this talk to us, and you were very generous to awake early in your side at 5 a.m. to give this talk. We thank you very much, and we appreciate your efforts to spreading out the word. At the end, I would like also to thank some people who contributed to the success of this event. First of all, I would like to thank my colleagues Saeed Maouch, who left for a technical problem, who left, my colleague Fouzi Biladam, my colleague in GeoLearn Hub, Yilla Samira, who helped making this event possible, my colleague Haddar Aisha, head of the tectonic team, for giving to this event its importance. I would like also to thank social media. For example, this event has been spread out by Maria Teresa Ramirez, which I greatly thank her for the efforts. Christoph Grutzner from Paleoseismicity.org, who made efforts to spreading out the word. And of course, we should, on behalf to GeoHazard and GeoLearn Hub communities, thank the CRAG, represented by his director, for hosting the event in the library of CRAG. and for spreading out the word in the official website of CRAG. I hope, yes, I need also to thank Rahma from CRAG, who helped us designing the video, the introductory video, and we apologize for those who couldn't join us on the studio. Thank you very much, and hope this is not the last webinar with these with experts, and see you in the next webinar. Yes, thank you very much.
Goodbye.
Goodbye.
Thank you.
For all.
Thank you.
See you.
Monsieur
Thank you
Oliva,
very much.
suivez bien, Léa.
Thank you.
Monsieur Oliva, vous m'entendez?
Uh-huh.
Suivez bien, Léa.
Pardon?
Léa pousse, que devient
Ah, Léa pousse. Oui. Elle est en train de travailler dur.